My name is Hao Gan. I am an assistant professor from the Biosystems Engineering and Soil Science Department at the University of Tennessee Institute of Agriculture. I will discuss the potential use of machine vision to aid in cotton management. Cotton fields in the Mid-South are typically trafficked in season 6 to 8 times with little to no data collected during each event on crop status. We believe a tremendous amount of information could be gathered from each traffic event. During those traffic events, operators usually make visual assessments of the crops, and we often see differences in conditions like stands, crop color, plant height, canopy closure, defoliation, and so on. However, those differences are not quantified, so they rarely drive changes in management. For example, stand assessments during a thrift application could identify areas which may need to be spot planted. Crop color differences could drive targeted soil samplings and potentially shift variable rate nitrogen, potassium, sulfur applications. Plant height and canopy closure differences could support changes in nitrogen management or variable rate PGR applications. Defoliation and percent open measurements could drive variable rate defoliant and bowl opener applications. One of the reasons we think this is a good time to quantify those measurements is because of the recent technological advancements in image processing. It allows those information to be collected and analyzed inexpensively. Here I'm showing some examples of cotton crops having differences in their phenotypes or physical characteristics. For example, in this picture, you can see clearly there are some differences in canopy closure and plant height. And if you see more closely, you can also tell there are some slight differences in the crop color. Those differences may lead to defoliant applications being both too aggressive or not aggressive enough within the same field, as you can see in this example picture here. As I mentioned, machine vision technologies is one way that could help quantify in-field variability, and they have been used for many applications. For example, the top two pictures shows an example of using machine vision for immature citrus fruit yield mapping. So on the left, a robot was equipped with several cameras that were used to scan the citrus growth and to detect and count the fruit. And then those information was combined with GPS locations and then to create a georeferenced map of the immature citrus yield. The bottom two pictures shows another example that uses machine vision to detect strawberry flowers and fruit and create a map showing the flower distribution which were used to predict fruit yield early enough. And then it also shows the map. It also creates a map that shows immature strawberry fruit and mature strawberry fruit distribution in the field. So similar systems can be developed for cotton crops as well. The objective of our project is to develop a low-cost camera system for high-resolution measurement of crop phenotypes. And our first step was to measure cotton height and leaf color. In addition, we also compared cotton crops with different treatments. So what we did, we created a randomized and replicated small plot trial in Jackson. And we implemented 4 different treatments, which consisted of 0 pounds, 40 pounds, 80 pounds, and 120 pounds nitrogen per acre, and to generate a range of crop growth statuses. So in this picture, it shows the map of the 4 treatments. Each treatment has 4 plots, so we have a total of 16 plots in our study. At critical growth stages, we had a plot sprayer outfitted with a camera called Intel RealSense, and it trafficked the center of each 2-row plots of all the 16 plots. The RealSense camera is part of the vision system, which also consisted of a mini computer and LED lights. They were mounted on an adjustable metal frame. The frame allowed adjustment of the height of the camera and lights from approximately 3 feet to 8 feet above ground. And this enables the system to take images of the cotton plants of various heights. We also developed software that allows the operator to collect all needed data with just one push button. We collected both manual data and video data on 6 different days from July to September. Here are examples of the depth video data and RGB or color video data. And that was collected by this vision system. The software we developed also synchronizes the 2 types of videos, so they have a pixel-to-pixel correspondence. The RGB videos were used to analyze crop color using greenness index, and the depth videos were used to measure crop heights. The imaging system collected both color videos and depth videos. However, due to motion blur and the fact that the color camera used a slower rolling shutter, the quality of the color videos did not satisfy the requirements for calculating accurate vegetation indices. On the other hand, the depth videos were collected successfully. We created or developed Python algorithms to convert MP4 depth videos to true distances and to synthesize the data from continuous frames to generate cotton height with high spatial resolution. This figure shows an example of the height measures of a plot in late August. The horizontal axis represents the number of sample data points along the width of each 2-row. A total of 640 data points were collected along the width. And for the purpose of displaying clearly, we averaged every 3 pixels together, so ended up with 213 data points along the width or along the horizontal axis. The vertical axis represents the number of frames. And the legend of the picture shows the height in inches. So instead of taking 5 measurements manually in each plot, this imaging system could provide millions of data points for more robust analysis. The current limitation of the imaging system is the lack of GPS data, which is needed to create geo-referenced cotton height map. And this will be added this year, the year of 2022. As I said, we also collected manual data, and those data were analyzed to examine the effect of nitrogen application to cotton growth. And this table shows the final crop height. We also counted total nodes and the number of nodes above white flower. And there are significant differences in cotton height, growth rate, and total nodes between different treatments. As we can see, more nitrogen applications up to 80 pounds per acre resulted in better cotton production. In another word, resulted in higher growth rate and height and more nodes. But in the treatment of 120 pounds per acre, we did not observe improvements in those in the cotton production. In this year, the camera has been upgraded to have a global shutter for high-speed image acquisition. As I just mentioned, last year, a rolling shutter camera was used, which resulted in blurred video frames due to the motion of the tractor. Also, the height of the camera will be raised to at least 8 feet above the ground to reduce video blur. So the new camera is shown on the left. In addition to the upgrade of the imaging system, a color checker will be used to calibrate accurate color under various illumination conditions. Also, so the color checker is shown in the middle. And also a differential GPS receiver will be integrated and synchronized with the video frames. So the final goal is to generate georeferenced cotton height and the vegetation index maps. So that's all of my presentation. Thank you for your attention. And if you are interested in more information, please feel free to contact me through my email address. Thank you.